In part 2 of this series, we'll touch on the global warming phenomenon briefly and focus more on the sources of air pollutants. Thank you for watching, and I appreciate your support. Let's briefly explore global warming first. This graph is crucial for understanding the natural cycles of Earth's climate history, including ice ages and warmer interglacial periods. The recent sharp rise in temperature highlights concerns about the rate of current global warming compared to historical natural fluctuations. The data is sourced from Arbintanja and R.S.W. Vandelwall in a publication titled Global 3M Temperature, Sea Level and Ice Volume Reconstructions. It was published by the National Ocean and Atmospheric Administration, NOAA, on August 13, 2008. The provided URL leads to further metadata and details about the study, ensuring the credibility and traceability of the information. The vertical axis measures the average temperature relative to today in degrees Celsius, ranging from -20 degrees C to +5 degrees C. This shows how much colder or warmer it was compared to present temperatures. The horizontal axis represents time, spanning from 1 million years ago to the present. This is broken down into 100,000-year increments, allowing us to observe temperature changes over a lengthy period. The line graph shows sharp fluctuations in temperature throughout the past million years. The line frequently dips into colder temperatures, indicated by values below 0 degrees C, which suggests periods of glaciation or ice ages. Peaks above 0 degrees C indicate warmer interglacial periods, where temperatures were similar to or warmer than today. The graph prominently features a sharp upward spike in temperature at its far right end, representing a recent and rapid increase in average temperatures. This notable rise is distinct from the more gradual fluctuations observed throughout the million-year timeline. Here's a more detailed analysis of this trend. Magnitude and speed. The sharpness of the increase suggests that the rise in temperature is not only significant, but has occurred over a relatively short period, especially when compared to the slower, natural climatic changes shown earlier in the graph. This implies a departure from the typical glacial and interglacial cycles that are characterized by more gradual transitions. Historical context. Historically, temperature changes on Earth have been driven by various natural factors, including volcanic activity, solar radiation variations, and changes in Earth's orbit and axis tilt. However, the recent spike surpasses natural variability norms, occurring much faster than any known natural rate in the past million years. Linked to global warming, the recent temperature rise correlates with increased concentrations of greenhouse gases in the atmosphere, such as carbon dioxide, CO2, and methane, CH4, which trap heat from the sun. The timing aligns with the Industrial Revolution, post which human activities, particularly the burning of fossil fuels and deforestation, have significantly increased these gas concentrations. Implications for climate. This rapid warming is linked to various changes in global climate systems, including more frequent and intense heat waves, melting glaciers and ice caps, rising sea levels, and more severe weather events. The graph's endpoint, marking contemporary times, serves as a visual representation of these unprecedented changes. Urgency for action. The graph serves as a stark illustration of the urgency required in addressing climate change. It underscores the need for immediate and sustained efforts to reduce greenhouse gas emissions and mitigate the impacts of global warming. This includes transitioning to renewable energy sources, enhancing energy efficiency, and implementing effective carbon capture and storage technologies. Looking at recent CO2 emissions helps us better understand the impact of global warming, connecting the dots 10 years at a time. This graph, titled Global CO2 Emissions, illustrates the annual global fossil fuel emissions, measured in billion metric tons of CO2, from the year 1880 to approximately 2020. The y-axis, vertical, represents the amount of CO2 emissions from fossil fuels, measured in billion metric tons. The scale ranges from 0 to 40 billion metric tons. The x-axis, horizontal, represents time from the year 1880 to about 2020. This allows us to observe trends in CO2 emissions over a long historical period. The trend line shows a general upward trend in CO2 emissions over time, indicating that the amount of CO2 released by burning fossil fuels has increased significantly since 1880. The slope of the line becomes particularly steep from around the 1950s onwards, reflecting the rapid industrialization and increased use of fossil fuels globally. Some historical events has an impact on this trend. Great Depression in 1930s. A slight dip or plateau in emissions growth, possibly due to reduced industrial activity and economic slowdown. End of World War II in 1945. A noticeable decrease in emissions. Oil crises, 1973 and 1979. These are marked by slight dips or slowdowns in the growth of emissions, corresponding to periods of energy crisis and the subsequent economic impacts. 2008 financial crisis. Another point where the increase in emissions temporarily slows, reflecting a global economic downturn that would have reduced industrial activity and energy use. Global COVID-19 pandemic. The graph shows a sharp decline in emissions, which is consistent with the global reduction in travel and industrial activity due to lockdowns and other restrictions. Current situation. The graph ends with a significant drop in emissions during the COVID-19 pandemic, but it is implied that this might be temporary, as economic activities resume. Source. The data is sourced from the Global Carbon Project, which provides detailed and reliable measurements of carbon emissions globally. This graph is useful for understanding how economic, social, and political events throughout modern history have influenced trends in carbon emissions. It also illustrates the challenges of managing and reducing CO2 emissions in the context of growing energy demands and global crises. About thickness of natural glaciers. One key indicator of global warming is the thickness of glaciers worldwide. Let's take a closer look at the curve. The curve displays the average cumulative glacier's thickness change over the period from 1940 to 2010, highlighting the trend in global glacier thickness during these 7 decades. The graph shows a clear and consistent decline in the average global mean of all glaciers, measured in meters. Below are key observations from the graph. Initial fluctuations 1940 to 1970. Initially, the graph shows a relatively stable line with minor fluctuations from 1940 until around 1970. This period includes a notable mass loss in the decade starting from 1945, but by around 1970, the mass balance of glaciers was nearly zero, indicating a brief period of near equilibrium. The relatively stable early decades could be misleading due to the limited number of glaciers monitored during this time, not providing a comprehensive global sample. Accelerated decline, post-1970. Post-1970, the graph depicts a consistent and significant downward trend. This period aligns with the global warming effects intensified by increased greenhouse gas emissions, as suggested by scientific literature. The trend reflects that glaciers began to shrink rapidly as a response to rising global temperatures. Dramatic loss 1975 to 2010. After 1975, the rate of glacier thickness loss accelerates dramatically. Each subsequent decade sees an increase in the rate of decline. Specifically, from 1996 to 2005, the mass loss was more than double that of the previous decade, 1986 to 1995, and over 4 times the rate from 1976 to 1985. This acceleration is a clear indicator of worsening global warming impacts on glacier volumes. Global perspective on glaciers. It's crucial to consider a broad set of data from numerous glaciers globally to avoid skewed perceptions from a limited dataset. The comprehensive decline shown in this graph underscores that globally, glaciers have been and continue to be affected by climate change, shrinking at an accelerating pace. Conclusion. The graph serves as a stark visualization of the rapid decline in global glacier thickness, offering a clear depiction of the long-term impacts of climate change on these crucial natural reserves. The data, sourced from a credible study by Zemp, M., and Gardner-Rohr, Isabel et al. 2008, emphasizes the importance of taking global, comprehensive data into account when assessing the health and trends of glaciers worldwide. This helps provide an accurate and unambiguous picture of how environmental changes are affecting glacier dynamics and, by extension, global sea levels and ecosystems. The next example illustrates the amount of carbon dioxide produced by a single car. This serves as an indicator of the broader impact of global emissions when you consider all vehicles, along with industries and other sources. It provides a snapshot of how individual contributions scale up to affect our planet. To give you an idea of carbon emissions, let's go through a simple example. Imagine an old car from 1997 that was driven until 2011, covering a total distance of 222,865 kilometers. Here's how we can estimate the carbon dioxide it produced. Assume the car's fuel consumption was 12.33 liters per 100 kilometers due to its age and inefficiency. Assume that 85% of the gasoline's weight is carbon. Consider gasoline's density to be 0.75 metric tons per cubic meter for the conversion from volume to weight. To find the total carbon consumed, we multiply the total distance by the fuel consumption rate, convert this to cubic meters, and then apply the gasoline density. With this carbon mass, we can calculate the CO2 emissions. Since burning carbon with oxygen produces CO2, we use the molecular weight ratio of CO2 to carbon, 44/12, to find the total emissions over 14 years. This calculation shows that the car emitted approximately 4.7 tons of CO2 per year. Please note how I carefully compare and cancel out the units in the calculation. By adjusting the calculation for a worse car with better fuel efficiency, say 6 liters per 100 kilometers, we can see how improving engine efficiency significantly reduces carbon emissions. This example underscores the impact that vehicle efficiency can have on reducing our overall carbon footprint. Let's explore the revised calculations to see just how much of a difference it can make. Please try repeating the calculation as a practice exercise and compare your results with mine. You'll find that a more efficient car produces almost half the carbon emissions, which logically demonstrates the impact of improved fuel efficiency. There are several other gases besides carbon dioxide that contribute to global warming. Methane, for instance, is released naturally by domestic animals during digestion. Chlorofluorocarbons, CFCs, once commonly used in refrigeration systems, also have a significant warming effect, though their use has largely been phased out due to environmental concerns. Additionally, nitrogen oxides are produced during the combustion of fuels in internal combustion engines and turbines. If you're interested in learning more about how these and other gases impact our climate, I encourage you to follow the provided web link for further information. So far, I explained the health effect of primary criterion pollutant. It is time to explain the sources of the pollutant briefly. Carbon monoxide, CO, is a colorless, odorless gas that can be a significant pollutant with harmful effects on human health. The main sources of carbon monoxide pollution include vehicle emissions. Automobiles, particularly those with internal combustion engines, are significant contributors to carbon monoxide pollution. Incomplete combustion of fuel in these engines produces CO. Industrial processes. Various manufacturing processes can emit carbon monoxide as a byproduct, especially those involving the burning of fossil fuels such as coal or oil. Residential heating systems and appliances that burn fossil fuels, like natural gas, oil, wood, or coal, can produce carbon monoxide if they are improperly installed, maintained, or if they malfunction. Forest fires and other biomass burning, natural processes such as forest fires, as well as human activities like the burning of agricultural residues, can release carbon monoxide into the atmosphere. Power plants. Facilities that burn fossil fuels for electricity generation, especially coal-burning power plants, can be substantial sources of CO emissions. Reducing exposure to carbon monoxide is crucial, especially in enclosed spaces, to prevent poisoning and other health risks. This involves ensuring proper ventilation and maintenance of all fuel-burning appliances and vehicles. Particulate lead, often found in the environment as a result of various human activities, comes from several primary sources. Industrial processes. Certain industrial processes release lead particles into the air, including metal smelting, battery manufacturing, and recycling facilities. Automotive sources. Although leaded gasoline has been largely phased out, residues from its extensive past use can still be found in soil near roads and in urban environments. Mining and metal processing. Mining operations, especially those extracting lead, zinc, and copper, can release lead particles into the surrounding environment. Waste incinerators. Facilities that burn municipal waste can emit lead particles if the waste includes lead-containing materials. These sources contribute to the presence of lead in the air, which can pose significant health risks, especially to children, when inhaled or ingested. Nitrogen oxides, including nitrogen dioxide (NO2) and nitric oxide (NO), are significant air pollutants that arise from several sources. Combustion engines. The primary source of nitrogen oxides is the combustion of fossil fuels in internal combustion engines such as those found in cars, trucks, and motorcycles. Industrial processes, various manufacturing processes including metal refining, cement production, and chemical manufacturing, can emit nitrogen oxides. Residential heaters and stoves, heating appliances that burn fossil fuels, like natural gas, oil, or coal, produce NOx, especially in poorly ventilated spaces. Agricultural equipment. High-temperature engines used in agricultural machinery also contribute to NOx emissions. Ship emissions. Large ships using diesel engines produce significant amounts of NOx, particularly affecting air quality in and around major ports. Biomass burning, wildfires, and controlled burns in agriculture can release nitrogen oxides into the atmosphere. Power plants. Facilities that burn coal, oil, or gas to generate electricity are major producers of NOx due to the high-temperature combustion processes involved. These sources contribute to the overall levels of nitrogen oxides in the atmosphere, leading to various environmental and health issues, including the formation of ground-level ozone and particulate matter, which can exacerbate respiratory diseases and other health problems. Ozone O3 is classified as a secondary pollutant because it is not emitted directly into the atmosphere, rather it forms through chemical reactions between primary pollutants under specific environmental conditions. This formation process is significantly influenced by high temperatures and strong solar radiation, which catalyze the reactions needed to produce ozone in the lower atmosphere. Here's an expansion on how ozone is formed from primary pollutants. Primary pollutants involved in ozone formation. Nitrogen oxides, NOx. These gases are emitted from combustion processes, such as those found in vehicles, power plants, and industrial boilers. They play a crucial role in the atmospheric reactions that produce ozone. Volatile organic compounds, VOCs, emitted from a variety of sources, including vehicle exhaust, industrial emissions, and chemical solvents. VOCs react with NOx in the presence of sunlight to form ozone. Environmental conditions supporting ozone formation. High temperatures, warmer temperatures accelerate the chemical reactions between NOx and VOCs. This is why ozone levels are often higher on hot summer days. Strong solar radiation, ultraviolet, UV light, from the sun, provides the energy necessary for the photochemical reactions that transform NOx and VOCs into ozone. Process of ozone formation. Photolysis of NO2. When NO2, a component of NOx, is exposed to sunlight, it splits into nitric oxide, NO, and a reactive oxygen atom, NO. Oxygen molecule reaction. The free oxygen atom, O produced, reacts quickly with an oxygen molecule, O2, in the presence of a third molecule, usually nitrogen or water vapor, forming ozone. Continuous cycle. NO reacts with ozone to form NO2 and oxygen, continuing the cycle under favorable conditions. This ongoing cycle of reactions keeps generating more ozone as long as sunlight and primary pollutants are present. Understanding these dynamics is crucial for managing and reducing ozone levels, especially in urban areas where vehicular and industrial emissions are high, and during periods of warm, sunny weather, which escalate the formation of ground-level ozone. Particulate matter, PM, in the atmosphere is composed of tiny particles and droplets that can be harmful to human health and the environment. The key sources of particulate formation can be categorized into two main types: primary sources, where particles are directly emitted into the atmosphere, and secondary sources, where particles form from chemical reactions involving gases. Here's a detailed look at these sources. Primary sources. Combustion sources. Vehicles, diesel and gasoline engines, emit fine particles as part of their exhaust. Industrial processes. Combustion in industries, such as power plants and manufacturing facilities, especially those burning coal or oil, contribute significantly to PM emissions. Residential heating and cooking. Burning wood, coal, or other solid fuels in households is a major source, especially in developing countries. Construction and road dust. Construction sites. Activities such as demolition, building, and the handling of cement and other materials generate dust. Road traffic. Vehicles stir up dust and particles from roads, especially unpaved ones. Agricultural activities. Tilling, harvesting, and plowing. These disturb the soil and release dust. Burning of agricultural waste. Open burning of crop residues is a significant source of particulates. Natural sources. Volcanic eruptions emit large amounts of ash and fine particles. Forest and grassland fires. Natural or man-made fires release large quantities of particles. Windblown dust from deserts and other dry, exposed land surfaces. Secondary sources. Secondary particulate formation occurs when gases emitted from various sources undergo chemical reactions in the atmosphere. Key contributing gases include sulfur dioxide (SO2), primarily from burning fossil fuels containing sulfur, especially in power plants and ships. Nitrogen oxides (NOx), from vehicle exhausts, power plants, and other combustion processes. Ammonia NH3, mainly from agricultural activities, including livestock and the use of fertilizers. Volatile organic compounds, VOCs, from solvents, vehicle exhausts, and industrial emissions. These gases react in the atmosphere under the right conditions of sunlight and humidity to form fine particulate matter like sulfates, nitrates, and organic particles. This process significantly contributes to the ambient levels of PM 2.5, particles smaller than 2.5 micrometers in diameter, which are particularly concerning for health due to their ability to penetrate deep into the lungs and enter the bloodstream. Understanding these sources is crucial for effectively managing air quality and reducing health risks associated with particulate matter. Sulfur dioxide, SO2, is primarily produced from processes that burn sulfur-containing fuels, especially coal and oil. Major sources of SO2 emissions include power plants. The largest source of SO2 emissions comes from fossil fuel combustion at power plants that burn coal or oil to generate electricity. Industrial facilities, industries such as metal smelting, petroleum refineries, and manufacturing that burn sulfur-containing fuels, contribute significantly to SO2 emissions. Residential heating, the burning of heating oil and other sulfur manufacturing fuels in residential furnaces and boilers, produces SO2, though this is generally a smaller source compared to power plants and industrial processes. Volcanic eruptions, natural emissions of sulfur dioxide can occur during volcanic eruptions, which release large quantities of gases, including SO2, into the atmosphere. Ships and maritime vessels. Heavy fuel oils used in large ships contain sulfur and can be significant sources of SO2 in coastal areas and ports. Efforts to reduce SO2 emissions include the use of sulfur-reducing technologies, switching to fuels with lower sulfur content, and enforcing regulations that limit the amount of sulfur dioxide that can be emitted from various sources. Volatile organic compounds are emitted from various sources, primarily due to their use in industrial processes, household products, and as fuels. Here are the key sources of VOC emissions. Industrial sources, chemical manufacturing, industries that produce solvents, paints, pharmaceuticals, and petrochemicals, release significant amounts of VOCs. Oil and gas industry extraction, refining, and processing of oil and gas are major sources of VOCs. Transportation, vehicle emissions, Cars, trucks, and motorcycles emit VOCs through exhaust and from fuel evaporation. Refueling. Gasoline evaporation during refueling of vehicles is a significant source of VOC emissions. Consumer products. Paints and coatings. These contain solvents that evaporate into the air during application and drying. Cleaning agents. Many household cleaning products release VOCs during use. Personal care products. Items like perfumes, hairsprays, and deodorants also contribute to VOC levels in the atmosphere. Building materials. Adhesives and sealants. Used in construction and home improvement projects, these materials often emit VOCs as they cure. New furniture and carpets. These can release VOCs from materials and glues used in their construction. Commercial and institutional. Dry cleaners. Use of solvents in dry cleaning operations is a notable source of VOC emissions. Printing services, particularly those using solvent-based inks, contribute to VOC emissions. Agricultural activity. Pesticides and fertilizers. Application of certain chemicals in agriculture can release VOCs into the atmosphere. These sources contribute to the presence of VOCs in the environment, which can lead to the formation of ground-level ozone and secondary organic aerosols when they react with other air pollutants under sunlight. Efforts to control VOC emissions include using products with lower VOC content, improving industrial processes, and regulatory measures to limit emissions from various sources. Thank you for tuning in. Wow, look at you, crushing this air pollution course like a pro. If you found this section enlightening and educational, show some love with a comment and hit that subscribe button. You know you want to. Stick around for part 3. It's going to blow you away.